I teach at the University of Massachusetts-Amherst, and I am director of the Professional Writing and Technical Communication program there. Writing for lay audiences presents its own interesting challenges, and one of them is to, as it were, translate scientific jargon into language that everyone can understand. I think many good books begin with simple questions, and sometimes the questions are the questions of children. And what began Weird Life for me, or what began me thinking about weird life, was a very simple question, a child's question, which is, how strange can life get? And a favorite book of mine as a child was Dr. Seuss's If I Ran the Zoo. It begins with a young boy visiting a city zoo. "It's a pretty good zoo," said young Gerald McGrew, "and the fellow who runs it seems proud of it too." "But if I ran the zoo," said young Gerald McGrew, "I'd make a few changes. That's just what I'd do. The lions and tigers and that kind of stuff they have up here now are not quite good enough. You see things like these in just any old zoo. They're awfully old-fashioned. I want something new." And Gerald McGrew, as some of you may recall, becomes a kind of a procurer of ever more exotic animals. Well, that is the search or thinking about exotic animals, I think, resonates with all of us. It has its own long history in mythology, but even the exotic animals in mythology are far, far outnumbered by what really exists on Earth, and many of them are, one might even stranger than our predecessors have imagined, or perhaps could have imagined. In any case, one begins to ask ultimate questions, which is, how weird can life get? How strange can it get? Are there limits to life? Well, strange to say, biologists have no strict definition of life. And the attempts to define life, or what separates an organism from a non-living entity, are old, perhaps as old as history. Attempts to define life have taken two approaches. One might say, is a functional approach. That is, you define an organism according to what it does. So we might say an organism grows, it breathes or it eats, it produces waste, it metabolizes, which is to say it has chemistry inside itself, which turns some molecules into other molecules, and we might say also that after a fashion it dies. The problem is, stars do all those things. Candle flames do all those things, and few of us would call stars and candle flames alive. We could add something else to the list, and we could say, well, an organism, to be alive, reproduces itself. Problem is, crystals reproduce themselves, and we wouldn't call crystals alive. Worker ants and mules do not reproduce themselves. Most of us would agree that worker ants and mules are living. So the functional definition of life seems to hit some roadblocks. The other way to define life has been a more materialist approach. That is to say, you define it not by what it does, but by what it's made of. Now, all life we know on Earth is made of certain chemicals. There's certain bunches of chemicals. All life we know on Earth has DNA or RNA as a long binding molecule. All of it has 20 or so amino acids as its base. All of it uses water as a biosolvent. That is to say, the liquid medium which enables complex chemistry. But it's not clear, and it wasn't clear to the authors of the National Research Council report, whether life necessarily needed those things, because one does seem to be able to make substitutions. So we were left not knowing, not having a good, strict definition of life. What would help us, perhaps, is not to come up with a definition, not a laundry list of components, but rather a theory of life. And to have a theory, you need another example. We have only one example of life. That is to say, life on Earth, life we know, is one example of life. All life we know, and this is important to understand, all life we know is related. All life we know descends from a single universal ancestor, one single-celled creature that existed billions of years ago. We know this because all life we know shares certain characteristics. It shares DNA or RNA, it shares those 23 amino acids, it shares the thousands of chemical pathways. And if we had another example of life, another kind of life that didn't have all those characteristics, we would have life that descended from another ancestor. That would be weird life. In the late 1980s and early 1990s, scientists began to discover on Earth extreme forms of life. There was life, there were organisms surviving in water that was very, very hot, 237 degrees Fahrenheit, far above the boiling point of water. These organisms were discovered at volcanic hydrothermal vents beneath the ocean. And scientists who discovered them were astonished. No one was expecting this. But these hydrothermal vents seemed to support an entire biological community. There were clams, there were fish, there were tube worms. This, in a manner of speaking, woke up a lot of scientists who began to see life living at extremes, extreme temperatures, extreme pressures, life living in salt lakes, life in the Dead Sea, life in the Great Salt Lake, life living, strange to say, even in Chernobyl, in the Chernobyl nuclear reactor, and living off the radiation, somehow repairing its DNA. They found life, all the assumptions were shown to be false. They assumed, among other things, life needed a substrate, something to move around on. And then they discovered bacteria living in clouds. No one had expected all this, but it made scientists, especially NASA scientists, exobiologists, that is biologists who think about life on other worlds, it made them understand that the possibilities were there, the possibilities were real. Lou Amendola is a founder and director of NASA Ames Astrophysics and Astrochemistry Lab. He's very interested in comets, and many astronomers have said, I think it's almost become a cliche, that what a comet is a dirty snowball, meaning it's ice and a little bit of rock and maybe some organic material. Lou Amendola says, though, that we really don't know what comets are made of. They're a long ways off, and they rather defy examination from a distance. And what he and his colleagues at NASA Ames have done is say, well, let's not worry about them out there. Let's just try to make our own, a homemade comet. And that's what they've done. And they've got a chamber that simulates deep space. It's about the size of a coffee can. And they removed the air from it. They lowered the temperature to a few degrees above absolute zero. And what they've done thereby is create a very good simulation of deep space. Then they introduced a few very simple molecules into it, and they bathed those molecules in ultraviolet radiation. They weren't expecting much to happen, but what they did what did happen surprised them a great deal. The molecules combined, and then they recombined and recombined again, and they became pretty complex molecules, so complex that they're called prebiotic molecules. This suggested what no one had really expected, that there are very complex molecules in deep space. Until recently, many astronomers had assumed that deep space was mostly empty. You might find a hydrogen molecule here or there, but there was no way for them to get together, certainly no way for them to form complex molecules. And now, many astronomers believe that the water on Earth and water on many of the moons of the outer solar system began with comets crashing into those surfaces. What Alamandola's research suggests is that those comets didn't just bring water, they also brought prebiotic molecules. There's a fringe idea on this, suggesting that comets may have also brought life. And that is to say, brought molecules that were a little more than prebiotic, that were biotic. In 2002, the National Research Council commissioned a report called The Limits of Organic Life in Planetary Systems. And that was the first time that anyone had thought seriously about these questions, or any group had thought seriously about these questions in some detail. And they concluded with a report that appeared in 2007 that was very ambitious. It tried to define life, and its provisional definition of life was a chemical system that involves Darwinian evolution. They tried as best they could to define the outer limits of life, and concluded that it is possible that life does not need to be based in carbon. It is possible that life does not need water as a solvent. It is possible that life might use a binding molecule that is other than DNA or RNA. These were ideas that appeared, of course, in science fiction for decades. But this is the first time that this had happened this is the first time we'd seen scientists produce a serious piece about this. NASA's strategy for looking for life on other worlds informally has been called follow the water, or find the water. That is to say, the assumption there has been that all life needs water as a biosolvent. But it's not clear, and it certainly wasn't clear to the authors of the NRC report, that that was the case. There were, they thought, other biosolvents possible. Ammonia, perhaps, liquid methane, perhaps, even other things. These would be compounds that would probably not be liquid on Earth. Earth would be too warm, but these would be compounds that would be liquid on places like Saturn's moon Titan, a very, very cold place. If that kind of life were discovered, life that did not use water as a biosolvent, life that used liquid ammonia or methane as a biosolvent, that life could certainly be most probably weird. That is to say, it would not have been descended from that universal common ancestor. It would be totally different than anything we have ever seen. And that prospect excites a certain subset of exobiologists. Astrobiologists, NASA astrobiologists, have been very excited in the last few years by the discovery of water. It does seem that the outer solar system is full of water. Scientists have long understood that there is water beneath the surface of Mars. Recently, water has been discovered, or evidence of water has been discovered flowing or having flowed recently on Mars. Likewise, Jupiter's moon Europa seems to have a subsurface ocean that has a volume larger than all the oceans on Earth combined. This, likewise, is very exciting. There seems to be prospects for liquid water beneath Saturn's moon Enceladus. There seem to be prospects for liquid water on many of the moons of the outer solar system, and all of this is very, very exciting. However, that sort of life would be life much like ours, and some scientists think that if life somehow traveled around a billion years ago, traveled around the solar system via meteor, then that life might be related to us. The exobiologists who think about weird life are not so much excited about Mars or Europa as they are about Saturn's moon Titan. What's exciting about Titan is that there are two possibilities for biosolvents there. One is an ammonia water slush, and one is liquid methane. What's also exciting about Titan is it has a thick atmosphere, and it has what on Earth we would call a hydrological cycle. That is to say, the liquids are moving around. But Titan is a very, very cold place. If life were there, any kind of life were there, it would certainly be very, very different. And it would most probably be weird. Scientists in recent years have found a great number of exoplanets, that is to say, planets that orbit stars that are not the sun. And every time an exoplanet is discovered that seems more Earth-like, then it captures headlines. What interests exobiologists who are particularly concerned with weird life are not the planets, the exoplanets that are Earth-like, but the exoplanets, strange to say, that are Titan-like. And what makes this question interesting and particularly provocative is that Titan-like planets may outnumber Earth-like planets by as many as 10 to 1. This is simply because red dwarf stars outnumber sun-like stars by about that ratio. If you have a red dwarf star and a Titan-like planet orbiting at a certain distance, you're going to have the possibilities for weird life, the kind of life on Titan that used liquid methane or an ammonia slush hybrid as a biosolvent. You're going to have many more examples of that kind of life than you would life that we know. Brandon Carter is a scientist who introduced a term and a concept called the anthropic principle. The anthropic principle comes in many forms. Its simplest form says that the universe in which we live seems to be designed to allow life. That in itself is a fairly provocative statement, among other reasons because it uses the word design. Carter and a number of other people who've thought about this don't all agree on what it means. But when we say the universe seems to design to support life, we are obliged to look at some of the fundamental constants, the natural constants in the universe. And it comes as a surprise to many non-scientists that these constants, some of them seem quite arbitrary. What do we mean by these constants? Well, there are 4 fundamental forces in the universe we know. Gravity is a force, the electromagnetism is a force, there is also the strong force and weak force, forces that work on atomic and subatomic scales. Strange to say, these forces have specific values. Gravity, for instance, has a specific value, and scientists do not understand why it isn't stronger or weaker. For years and years and years, scientists took it as a given. No one questioned, no one asked why until Carter did. And when he did, other scientists began looking at the other constants, not just the forces, but things like the weight of a proton, or the weight of a neutron. These two are specific weights. What's strange and provocative to Carter and many other people is that if you changed these values, that is, if you made gravity a little stronger or a little weaker, or the weight of a proton a little lighter or a little heavier, you couldn't have the universe we have. Gravity were a little weaker when the universe began. When the universe began its inflation, it would have just continued its inflation. And it would have continued its inflation unchecked. And we'd have a universe of hydrogen atoms, nothing like chemistry, let alone life, let alone us. If the force of gravity were a bit stronger, then it would have imploded. It would have collapsed on itself very soon after its initial inflation. And again, we'd have no universe. So one conclusion of this leads us to thinking about the multiverse, that it's not so much that many people who hold with multiverse theories, that is, theories that there are many universes. We're only one. There are many, perhaps an infinite number. People who hold with that idea believe that most of these other universes are barren. They are empty of life. They are just fields of loose hydrogen, empty space, a variety of universes in which life would be impossible. We just got lucky, as it were. What's this have to do with weird life? A few years ago, a group of scientists suggested that if you adjusted not just one parameter, but a couple of parameters of these values, particularly adjusted the weak force, you still could have a universe with life in it. It would be very different sort of life. It would be undoubtedly weird life by the definition we've been using here, but it would work.